For most of human history, we believed that the radiant glow of a fire, or the light from the sun, was the only form of radiant energy in the universe. If our eyes couldn't see it, it didn't exist. But the sliver of color we call visible light is actually just a tiny window into something much larger. Every wave on this vast spectrum begins with the exact same physical trigger, an electrical charge that is accelerating or oscillating. This animation shows exactly how that charge behaves. As it accelerates, it creates an oscillating electric field in space. That changing electric field immediately generates a magnetic field perpendicular to it, which in turn generates another electric field. They feed off each other, constantly regenerating to push the wave through space. And whether it's a radio signal or a ray of sunlight, it moves through a vacuum at the exact same velocity, the speed of light, roughly 300 million meters per second. Even though our eyes are blind to almost all of it, the empty space around us is packed with these self-sustaining ripples. To understand how these ripples operate, we just need to look at two measurements: frequency, how many wave cycles pass a point every second, and wavelength, the physical distance from one wave peak to the next. This vector diagram illustrates the single rule governing every electromagnetic wave. Frequency multiplied by wavelength always equals a fixed constant, the speed of light. Because that speed limit never changes, those two variables are locked in an inverse relationship. If you increase the frequency, the physical distance between the wave peaks has to shrink to keep the math balanced. This comparison chart shows just how extreme that shrinking gets. At one end, we have waves that span a full kilometer, taller than any skyscraper. At the other end, they are so compressed they fit inside an atomic nucleus. That simple mathematical balancing act dictates exactly how different waves interact with the physical world. At the far left edge of the spectrum, we find radio waves. These have the lowest frequencies, which means they stretch out to immense wavelengths. This spectral map highlights the territory we use for global communication. AM radio sits down around 500 kilohertz, while FM and your cellular phone operate further up, nearing 1000 megahertz. We produce these massive waves by forcing electrical charges to move back and forth along giant conducting wires, like broadcasting antennas. Moving just to the right, we jump into the gigahertz range. Here, the wavelengths shrink significantly, bringing us into the territory of microwaves. Because these waves are shorter, they easily reflect off smaller physical objects. This makes them perfectly suited for radar systems to track the precise location of aircraft and vehicles. But if you tune those microwaves to a highly specific frequency, you get a completely different interaction. This visualization shows water molecules absorbing microwaves. Because the wave's frequency matches the water's natural resonant frequency, the molecules absorb the energy and vibrate violently. This cross-section shows how your kitchen appliance harnesses that specific physics. A magnetron generates the waves, they bounce off the metal walls, and translate electromagnetic energy into the kinetic motion that cooks your food. The difference between a local radio broadcast and a hot meal is purely a matter of frequency and resonance. Shift the frequency a little higher, and we reach infrared. We often call these heat waves because they are generated by the thermal motion of molecules inside hot bodies. We can see this heat exchange constantly on a planetary scale. This simulation tracks the cycle. The Earth's surface absorbs high-energy sunlight and then re-radiates that energy outward as longer wavelength infrared. Molecules like carbon dioxide and water vapor happen to absorb these specific infrared wavelengths, which traps the heat and maintains the planet's average temperature. Just past infrared, the wavelengths compress down into a tiny window between 400 and 700 nanometers. This is the visible spectrum. But notice how there is no sharp division or wall here. As the camera moves along the gradient, the waves compress closer and closer until they cross the threshold of what our eyes can detect, smoothly fading from invisible heat into red light. Nature didn't draw a hard line between infrared and visible light. The categories we use are just human labels mapped over an unbroken physical reality. If the underlying physics of a radio broadcast, a hot stove, and a beam of sunlight are exactly the same, why do they feel like completely distinct phenomena to us? The answer lies entirely in how we detect them. We classified the spectrum based on our own biology and the technology we built. Look at this comparison. To capture a radio wave with a massive physical length, we have to build an equally massive structure to catch it, like a giant metal satellite dish. But to detect the tightly compressed waves of visible light, we only need the tiny, specialized photoreceptor cells inside the human eye. They belong to the exact same family. The entire spectrum is a single, continuous physical mechanism, behaving differently purely based on how its specific wavelength physically strikes the matter around it. There is no strict boundary between light and radio. There is only one spectrum, manifesting in many hidden worlds.